Okay, got that going. Yeah, we're starting chapter 9, I think. Yeah, 9. And chapter 9, the big idea is moment of inertia is a big idea that we're focusing on in this class. And I told you that one way that we can intuitively think about the mass of an object is we can think about the mass of an object as its resistance to accelerate. The more massive an object is, the harder it is for me to get it moving, to accelerate it forward. Imagine there was some big, heavy steel box on perfectly frictionless ice. It has a ton of mass, so it's really hard for us to get it started accelerating. And then once it's accelerating, it's also really hard to get it's hard for us to accelerate it. That's the best way to say it. It's hard for us to accelerate. It's hard for us to get from not moving to start moving. So I'm going to rephrase that now. I'm going to say that we can view mass as an object's resistance to linear acceleration, to move linearly, to accelerate in a linear direction, straightforward. Moment of inertia, intuitively, is an object's resistance to rotate. The more inertia an object has, the harder it is to rotate it. So if you think about this, when I hold this like this, and I'm going to rotate around the axis going right to the top here, when I rotate it like this, that's real easy for me to do, relatively speaking. I can do a full rotation with hardly any work. Now imagine I try doing an axis like this, going through right here. Now that's a lot harder to twist, and it takes a lot more effort for me to do a half rotation this way than it takes me to do a full rotation this way.
Yeah.
Why is that? Intuitively, tell me why it's so much harder for me to move it this way than it is for me to move it this way. What do you think?
Your mass or your radius is a lot bigger.
Because your radius is bigger. So you have more mass further away from the axis that you're trying to rotate it on.
The radius.
So think about axis through the top of this thing. This point right here is one of my furthest points away from the center, where I'm rotating it from. So my biggest radius, meaning distance from where I'm rotating it from, is that big for right here. Okay. And then for all this bar part, the radius is very, very small for how I'm rotating it. When I then go and rotate it like this, look how far out this mass is from where I'm rotating it. That's a long ways out, and so that's a lot harder to rotate. I don't know, you work job sites, you probably notice if you have like a 2x4, you can take a 2x4 and you can spin it really fast, decently fast, just holding it straight up. But then when you take a long 2x4 and you turn it this way and you swing it that way, a lot harder. Takes a lot more energy.
Yeah.
So you're right, you've got the good intuition, that's great. Good intuition for the mass is further away, and so for some reason, it takes more energy to move it. Another way to think about it, since the mass is further away, think about how fast this mass at this very furthest point out here is moving, the actual velocity of it. That has a lot more velocity than this mass has when I just spin it like that.
Has a lot more speed.
Velocity.
Okay.
Imagine, let's think about it from a bird's eye view. Imagine that you're on a, what do they call those things that kids play on that like spin? Oh, we'll just say a merry-go-round, but that's not what I'm thinking of. Imagine you're on a merry-go-round that has a radius of 1 meter, and you're standing right here. In one rotation, let's say it spins around once every second. Takes 1 second to spin around. You with me? Mm-hmm. You're going 2 pi meters per second. That's your speed. Mm-hmm. Your speed would be 2 pi meters per 1 second, right?
Yeah.
Now imagine that I made that merry-go-round. Instead of having a 1 meter diameter, I suddenly gave it, I don't know, like a 5 meter diameter. So now the merry-go-round, here's the outer part of it. We won't draw the whole thing going around. And now you're standing out here. And now you're at 5 meters. And it's still 5 meters. And it's still going around once per second.
Yeah. Well, it doesn't make sense for it to go around for 1 second for 1 meter and then 1 second for 5 meters. You're just saying in this made-up scenario, that's the speed?
Yes, I'm saying imagine I take this thing, when I have this, and let's say in 1 second I turn it a fourth the circle.
Yeah.
Now let's say I've got it this way, and in 1 second I turn it a fourth the circle.
Well then, yeah, it makes sense that that is going faster.
Perfect. No, they're both, oh yes. So the outer point here, now, if I want to turn this 90 degrees, this outer point had to move a lot more distance.
Yeah.
So if I turn it 90 degrees in 1 second, it had a much faster speed than if I'm holding it this way and I turn it 90 degrees in 1 second.
But your longer one takes a lot more work and a lot more energy to turn.
That's the point. So the kinetic energy of this most outer point, there's a lot more kinetic energy that that point has when I rotate like this than when I rotate like this. And since it has more kinetic energy, it takes more work, hence it's harder. I'm not saying those are both the same hard. I'm explaining to you why it's harder. Why is it harder? You have to give it more kinetic energy. And so it actually takes more work. Whereas this is easy.
Yeah. Okay.
So that is the moment of inertia of an object. The moment of inertia of an object, notice you need to talk about both the object and the axis you're going to rotate it about. Otherwise it doesn't make sense to talk about.
Yeah.
But once you have an object, and once you have an axis that you're talking about, you can then talk about the object's moment of inertia with respect to that axis.
Can we go over what inertia means again?
Moment of inertia.
No, just the word inertia.
Resistance. Or if it's got it, it keeps it.
An object
Hard to change.
stay in motion.
Yeah.
Okay.
So its moment of inertia, its resistance to spinning, is what we're talking about today. And so, very similar, notice, and you already got the important point. You got the important point that an object's resistance to spin doesn't just have to do with its mass. More massive objects are harder to spin, but even if you're talking about an object of the same mass, it has way more moment of inertia when you try to spin it one way than when you try to spin it another way.
Way more moment of inertia?
Yes. This object has much more moment of inertia. Its moment of inertia is far greater when I have its axis right here and I rotate it this way than when I have its axis right here and I rotate it this way.
So moment of inertia is the unit of measurement.
Moment of inertia will be a property that some object has relative to some axis. Just like mass.
Okay.
It just also depends on an axis. It depends on both the object and the axis. It depends on both the mass that the object has and how that mass is distributed. That's the fundamental intuition for moment of inertia.
How do you know which side you want to measure? How do you know if you're measuring it spinning from the end of the blue tip?
You add up all the mass. I calculate it for every little bit of mass. I calculate this atom's moment of inertia, this one's, all of it, and I add it all up.
Okay.
So we'll do an actual calculation like that, but I just want to give you intuition for the big idea of what we're covering today. That's intuition for the big idea of what
That's the whole chapter?
It's talking about moments of inertia, calculating moments of inertia. Yes. And then next chapter will be conservation of angular momentum, which is the same way that we learned that linear momentum is conserved. Angular momentum is also conserved, meaning a spinning object, however it's spinning, will continue spinning that way. Kind of. It's why if I'm spinning in a chair holding out weights like that, and if I pull the weights in, I suddenly get a lot faster, and then if I put them back out, I get a lot slower. That's conservation of angular momentum. Very closely related to this moment of inertia idea.
Sorry.
So, those will be the next two chapters. They complement each other quite nicely. So before we jump into actually calculating some of these momentums and giving you equations for momentums, let's just go back and restart where the author actually starts. And finally, the author has a conversation that we had a long time ago, but let's rehash the conversation since the author's now finally having the conversation.
Okay.
So going back to talking about motion around a circle. Motion around a circle, circular motion. I could say that you start at some angle theta naught here, and that you move to some angle theta 1 here. So talk about some angular displacement, delta theta. Delta theta equal to theta 1 minus theta naught. Okay? So you move from this point to this point. Notice that whatever we're talking about has an angular displacement. Oops, minus theta naught, not theta 2. And we can also talk about the displacement along the arc. If I call this distance along the arc from here to here x naught, and I call this distance from here to here x1, then your displacement is x1 minus x naught or delta x, right?
Yeah.
Mhm.
Something that we've seen 100 times. Okay, some definitions that we've already been using, but now the author introduces them, so I'll let you remind you of it. So now we're going to define a notion of your angular speed, alpha, or omega, sorry. Omega. Your average angular speed is your angular displacement divided by time. If this right here were 1.5 radians, so the angular displacement between here and here were 1.5 radians, and I did that in 1 second, my angular speed, or my average angular speed, is 1.5 radians per second.
Okay.
Right?
Yeah.
I can talk about how fast I'm going around the circle in terms of my angular displacement, like 2 pi radians per second.
Yeah.
Or I could actually talk about the arc length of the circle and how fast I'm going there, but then we're just talking about regular velocity.
And that's
Or
not
regular
bad,
speed.
is it?
That's different. Because that depends on the radius of the circle.
So, what's the difference between just the arc length speed and the angular speed, and why do you care?
So angular speed is how many radians per second you're going.
How many radians per second? Okay.
Yes. Regular speed, your speed on the arc length, is meters per second.
So
Right? If I'm on, going back to this example, if I'm on this little Ferris wheel, or on this little merry-go-round, and if it is doing 1 rotation every 2 seconds, my angular speed is 2 pi radians per second. Similarly, if I'm standing out here on this massive merry-go-round, and it's going around once every 2 seconds, my angular speed is still 2 pi radians per second. But those have very different linear speeds.
Okay.
You see that?
Yeah. So
They're just talking about 2 different quantities.
So it's what you care about in the on the circle, I guess.
Well, it's just something that you know. So if I've got some big wheel rotating, and the big wheel is rotating once per second, then I know your angular speed, no matter where you're standing on that wheel, is 2 pi radians per second. Your linear speed changes depending on where you're standing on the wheel.
Yeah.
If you're standing close to the center, your linear speed is small. If you're standing out here, your linear speed is small. But for the whole wheel, the angular speed is the same. It's constant.
So why
Not
is
necessarily
that?
constant, but the same.
Why is that beneficial?
Because maybe we just imagine something you can measure. You've got some wheels spinning on a bike, right?
Yeah.
And maybe you've got some card attached to the middle. It's real easy for me to time and count how many revolutions that bicycle wheel's making per second, so I can calculate omega really quick. It might be harder for me to calculate, okay, what's the linear speed, though, of that card right there? It's just a useful quantity. Something you can talk about, something you can measure. And we can often use omegas to figure out velocities.
How is omega related to velocity again?
We'll see.
Okay.
So, wrap our heads around the definitions for a second. So, our average angular speed is just our angular displacement over time.
Mm-hmm.
And then take the limit as our time gets arbitrarily small. In other words, we take the derivative. So, omega then is just the derivative of theta with respect to time.
Okay.
And you might have noticed, I didn't put it up here anywhere. We'll erase the bottom half of the circle since we don't really need it. We defined, reminding us of some things we've been using for a long time, your average velocity was delta x over delta t. Your instantaneous velocity was dx dt. Your average acceleration was change in velocity over time. And your instantaneous acceleration was dv dt, or the second derivative of x with respect to time. Right?
Yeah.
Those are our super old definitions from like class 1. Okay. So, you see how angular speed or average angular speed and average velocity are very closely related. Same with velocity and angular speed. Your average velocity, we also have your average angular acceleration. Sorry, I should have said this one first. What's your average angular acceleration? Well, that's equal to your change in angular speed over time.
Yeah, that makes sense.
Makes perfect sense, right? And then alpha then is just the derivative of your angular speed with respect to time, or in other words, it's the second derivative of your angular position with respect to time. Good? Now, how can we connect these equations to these equations? That comes from noticing something clear back here when we were first defining what's a radian. How do I get from an angle, this angle, how do I go from theta to figuring out this arc length right here? And that's this right here. X naught is equal to theta naught times r, if theta is in radians.
If theta is in radians.
Yes,
So
we
it's
always
not
measure theta in
actual
radians.
degrees. Okay.
Yes, so if theta is measured in radians, then x naught is theta naught times r, and x1 is theta 1 times r. Or in other words, if you take theta and you multiply it by r, you're left with x. You're left with your displacement.
Okay.
Your linear displacement, we'll say, to distinguish from angular displacement. So, I know, well, so we have it for x. How do I get from a theta naught to an x naught? We multiply by r. Okay, so let's come down here and look at now at average angular speed. Let's take average angular speed and multiply by r and see what we get. Well, when I take average angular speed and I multiply by r, that's equal to delta theta over t, that's just what average angular speed is, times r. But delta theta times r is delta x.
And that makes sense.
And delta x over delta t, that gives you your average acceleration.
Average velocity.
Or average velocity, thank you.
Yeah.
Similarly, if you take it in the limit as delta t goes to 0, you'll get this equation. Omega times r gives you velocity. And similarly, we have our average angular acceleration. When we multiply that by r, that's the same as taking our change in our average angular speed over time times r. But we just barely found out that delta omega times r gives you a change in velocity.
How did we find that out?
Right here.
Oh, okay.
So then it gives you the average acceleration. Take in the limit, alpha times r gives you your acceleration. And your tangential acceleration, meaning your acceleration that changes your speed. This isn't the part of acceleration that changes your direction. We already calculated that. That's centripetal acceleration. Remember, acceleration is change in velocity, so there's two types of acceleration. There's an acceleration when you change the magnitude of a velocity. That's what we mean by tangential acceleration. And there's acceleration when you change the direction of a velocity. That's what we mean by centripetal acceleration. So here we're just talking about the tangential acceleration. We've already handled centripetal acceleration a lot earlier. Right? Good?
Yeah.
Okay. So now, let's ask ourselves a simple question. Let's assume, let's see what we know about some system. So we've got some rotating system, some wheel spinning or something like that.
Okay.
What are all the things we instantly know for free if we know that its angular acceleration is constant? What can we conclude if we know that alpha is constant? The angular acceleration is constant. And remember, 0 also counts as a constant.
Well, you know, if acceleration is constant, then you can use a kinematic equation, so wouldn't it still apply?
Perfect. So if I know that alpha is just a constant alpha, integrate, what's the integral of alpha? Omega. Right? Because, how was alpha defined? Alpha was a derivative of omega with respect to time. So if I were to take the integral of alpha with respect to time, it's going to give me omega.
Yeah.
And integrate alpha with respect to time, that's just going to be multiplying by t plus a constant.
Didn't we already do this?
Yes, we already did this. And then if we integrate this with respect to time, well, the integral of omega with respect to time is theta, so I get a our theta function. And when I integrate this with respect to time, that's going to become a squared, and then you bring down a 1/2, so 2, bring down the 1/2. And when I integrate that, that's just going to be a constant times t, and then plus our constant. Right?
Okay. In the next one, you have omega plus omega naught, and then in your kinematic equations, you have velocity minus velocity naught.
Yep, that's a typo.
Oh, okay.
Because here's what this says. Your 1/2 v plus v naught, this is your average velocity. Your average velocity times time gives you your displacement.
Yeah.
Makes perfect sense, right? So same thing over here. So just walking you through a couple of those, but yes, we derive these the exact same way we derive the kinematic equations.
So it's just the kinematic equations on circles.
It's the same concept as the kinematic equations. The kinematic equations essentially said, if I know that the second derivative is a constant, what do I know? And we know these equations. It had nothing really to do with velocities, or with accelerations, or with displacements. All it had to do is you had a function, you had its derivative function, and you had a second derivative function. If the second derivative function is a constant, what do you know about the other functions? They're related in this way.
Okay.
And so this is another application of the exact same concept. Talk about different physical ideas, but identical mathematics. We just change the variables.
How does that work? Like, how can you use... Never mind, it makes sense.
Okay. Anything else weird there? Okay. So the big takeaways there. Takeaway number 1. To get from an angular displacement to a linear displacement, multiply by r. To get from an angular speed to a linear speed, multiply by r. To get from an angular acceleration to a tangential acceleration, or we'll say a linear acceleration, multiply by r. To go the other way, divide by r. To get from a linear displacement to an angular displacement, divide by r. To get from a linear speed to an angular speed, divide by r.
Yeah, that makes sense.
That's big takeaway number 1. Big takeaway number 2, kinematic equations hold for alpha, omega, and theta the same way that they hold for AVX.
Okay.
Good?
Mm-hmm.
Okay, so that was just rehashing a conversation that we had forever ago, but remind you of that conversation because we're going to do a lot of stuff with rotations now.
Okay.
So let's now get to talking about moment of inertia. And I've already tried to motivate it for you a bit. We're thinking about fundamentally the reason that it's harder for me to rotate this way than for me to rotate it this way is because it takes more energy. When I rotate this, if I were to rotate them at the same speed and rotate this way at the same speed, when I rotate this way, the objects, the masses of the objects have way more kinetic energy. And so it takes way more work to rotate it at the same speed.
Yeah.
Right? So it's tied with this concept of kinetic energy. So you'll intuitively we know, okay, so what we're interested in then is calculating the kinetic energy of a rotating object. So let's do that. Let's calculate the kinetic energy of some rotating object like this.
Okay.
You with me so far? Let me get a chair. So here's our fundamental idea on how we're going to calculate the kinetic energy of something like this rotating wheel. We're going to take a little piece of the wheel and pretend that that's a little point mass on the wheel. I drew it as kind of a big square, but imagine that square is much, much smaller. It's just so you can see it.
Point mass, okay.
I'm going to take that little part of the wheel, and I'm going to calculate its kinetic energy. And then I'm going to take this part of the wheel and calculate its kinetic energy, and this part, and this part, and this part. And I'm going to do that for every part of the wheel and add up all their kinetic energies, and that gives me the total kinetic energy of the wheel, right?
So you would just do it for one, and then you would, what, put an integral on it?
Integral, if we're going to go, ultimately we're head towards integrals.
Okay.
But for now, let's just say that we're breaking up into 100 pieces, 1,000 pieces, some number of pieces. We won't say infinitely many yet.
Okay.
So if I want to calculate the kinetic energy of this thing, then for the first little piece, for our mass m1, then that's going to be 1/2 m1 times v1 squared, right?
Yes.
And then we might have our next little piece of mass. Maybe that's a little piece of mass right here. Here's m2. And it's going to have a much smaller radius r2, and it's going to have a much smaller velocity v2, right?
Okay.
But, once again, we just add up its kinetic energy too. So 1/2 m2 times v2 squared. Plus, and we do that for all the pieces of mass. I just arbitrarily chose 2 out there. But for all the 100 or 1,000 pieces or however many pieces we have, we add up all their individual kinetic energies, and that's going to give us the kinetic energy of the whole system, right?
Yeah.
Okay. So now, the next thing I'm going to do, so this whole sum then is equal to, what do I want to do first? Do I want to replace the velocities or factor? We'll replace the velocities first. So how do I get v1 squared? So this is the same thing as 1/2 m1 times, what can I replace v1 squared with now? How can I rewrite that in terms of omega?
Just divide it by r
It's just
Right.
omega
squared.
Yeah, I'm looking at that.
omega times r. So I can rewrite this as
Omega
omega times
I see.
r1 squared.
Okay.
You with me?
Mm-hmm.
Similarly, we can have plus 1/2 m2, and it's going to be omega, same omega, but different radiuses.
How do you get the same
Does
momentum?
omega change?
Omega, the angular speed of the wheel, is the same no matter where you are on the wheel.
Okay. Yep.
If this wheel is rotating once per second, then no matter where you stand on the wheel, you are going around it you're going 2 pi radians per second. Your linear speed changes a lot, but your angular speed is the same no matter where you are on the wheel. The whole wheel is rotating at the same rate.
Mm-hmm.
That makes sense.
Okay, so same omega for each of these, different radiuses, different masses. You with me?
Yeah.
So this is equal to, then I can pull out, notice that every single one of these have a 1/2 term. And
an omega, right?
and an omega squared term.
Okay.
So I'm going to pull the 1/2 out in front of everything. So we have 1/2 times, and then we're going to have m1. Let's pull out the omega squared too. Although we'll change the order in a second.
Don't you have to factor it?
Yeah, I'm factoring out a 1/2 omega squared from every single one of these. And that's going to be left with, so what am I left with in this term? I'm left with an m1 times r1 squared.
isn't omega times r squared?
No, it would be if
It
it
was
was
have to
omega squared times
If it was
r1
plus.
squared. This is the same thing as omega squared times r1 squared.
But what about like omega times r and r times omega?
That's only pluses.
Oh, okay. I see where you're
Oh,
yeah.
yeah, that's a dot. Okay. So, when I factor out of this a 1/2 omega squared, I'm left with an m1 r1 squared, right?
Mm-hmm.
And then plus, for this one, I'm left with a m2 r2 squared. And then we have plus m3 r3 squared. Plus, etc. You with me?
Mm-hmm.
Yeah.
Now, I'm going to rewrite that sum there. I may just use summation notation. So it's equal to 1/2 omega squared times the sum. Remind you of our sum notation. From I equals 1 to some number n, we don't know, of m sub I times r sub I squared. Right?
Yep.
Okay. So then what is the moment of inertia? The moment of inertia, I, is that quantity right here. I is equal to the sum from I equals 1 to n of m sub I times r sub I squared. That is what we call the moment of inertia. You take the mass, you add up all the masses, times how far they are from the radius you're rotating around, squared. Which notice that you already had this intuition. There were two things that went into account when we were talking about the moment of inertia of this thing. One, how much mass it had, and two, the radius, the distance the mass was from where we were rotating.
Yeah.
Here the radius was smaller, here the radius was bigger. And so, that appeals very much with our intuition. This is saying the further away the mass is, the higher up the moment of inertia goes, and the more mass it has, the higher up the moment of inertia goes.
How about your 1/2 omega squared?
That was for the kinetic energy. So just this term right here is what we call inertia. So now when I calculate the kinetic energy, that is equal to 1/2 your moment of inertia times omega squared. And notice you're used to seeing K is equal to 1/2 m times v squared. Here's your kinetic energy due to your linear motion. Here's your kinetic energy due to your rotation. And you see that the moment of inertia acts the exact same way as mass, and your angular speed acts the exact same way as your velocity.
That's pretty cool. Okay.
Okay? So one crucial theorem, and then we'll take our break, talk about tests, and then we'll finish up next time.
Okay.
So let's go over this amazing theorem. And this amazing theorem has to do with trying to calculate the moment of inertia. Ignore the bottom part of this thing for a second, and imagine that this is a perfect cylinder, something that we're used to working with.
Okay.
You might think that calculating its moment of inertia as it rotates right around its center, that's going to be pretty easy, right?
Yeah.
But now imagine that I'm rotating it around some point right here. So I'm rotating it like this now, around some point in the middle. That's going to be much harder, right?
Yeah, because your radius is bigger.
Because the radius is weird. It's like looking from a bird's eye view. Looking from a bird's eye view down in a cylinder, if I'm just rotating it about its center, then the radius of this mass to the center point is just the radius of the circle from the top. That's easy to talk about. Now imagine that I had this cylinder and I'm rotating around this point right here. So this whole cylinder is rotating around like this. Now talk about the radius of this point right here, the distance from here to here. That's much harder to talk about.
Yeah.
Mm-hmm.
And if we had to do some integral where we were adding up all these distances and multiplying them by that, that's way harder than if we were just multiplying by the radius. It turns into a very ugly integral.
Wait, so you're saying it's not just multiplying the radius of the thing outside of the cylinder? And
I'm saying
the
calculating the moment of inertia for a cylinder rotating around its center. Since everything's nice and centered, the integral is going to be nice and easy.
Yeah.
If we were to try and do it for calculating it rotating around a point like this, that gets a lot uglier.
How does it get ugly? I don't see.
Because I'm going to have to come up with a function that describes where the mass is for everywhere on the cylinder. And when I'm rotating around the center, then that function is just the distance from the center to here. It's just the radius it is out.
So why isn't it just the radius out to that point outside of it?
Let me make this much simpler for you. This isn't exactly what we'll be doing, but it gives you good intuition. So imagine that I've got a circle here and a point in the middle. And let's say that you know that the circle has radius 3. And if I were to ask you, how far is this point right here from the center of the circle? And if you knew its angle theta, you could figure that out real easy.
Yeah.
Now if I asked you to figure out the distance from that point to a point out here, that's a much harder question for you to answer. You can still figure it out, but the point is it's ugly.
Yeah.
Whereas this was really simple. It's just, its x-coordinate was r cosine theta, and its y-coordinate was r sine of theta. For that, you have to do some calculation between figuring out where this is, figuring out where that point is, and then using a distance formula to talk about the distance between them. And it gets ugly.
I see.
So similar things when we're setting up our integrals. It's real easy for us to talk about calculating the moment of inertia when an object's rotating around its center of mass. Typically, it's a lot easier for us to talk about rotating around its center of mass than some other point. So it's easier for me to talk about this rotating around its center of mass than for me to talk about it rotating around some point over here. This theorem that we're going to prove gives us a way so that even if I was talking about this thing, instead of rotating around the center of mass, it's rotating around a point over here. This theorem gives us a really easy way to make that calculation, where the hard part is just calculating its moment of inertia around its center of mass. That's what the theorem does.
Gotcha.
It makes all that, no matter where you had to rotate it around, we can reduce it so that the only hard part is figuring out its moment of inertia around the center of its center of mass, and then outside that, the rest you kind of get for free. So here's initially what we're proving.
Okay.
Your moment of inertia rotating around any point is equal to your moment of inertia around your center of mass plus the mass of the object times the distance squared between the point and the center of mass. And it turns out it's that easy. Calculating that is going to be the hardest part of this equation.
Yeah.
The total mass, that's going to be easy. Calculating the distance between 2 points, that's going to be easy. But calculating this integral is going to be the hard part. But it's still going to be a lot easier than if we had tried to calculate this integral right out the door. So, you feel like you understand what it is that we're proving and why this is going to be so useful?
I don't see why it's useful.
It's going to make so that we don't have to do integrals where we have to add up the distance to this point over and over again. Because look, when I'm doing an integral, what am I going to do? Here's what I would have to do over and over again. If I'm rotating around this point, I have to take for all infinitely many masses, for any random mass here, I would have to calculate its mass times this distance squared. This one, I'd have to do its mass times this distance squared. For this one, I'd have to do its mass times this distance squared.
Oh, I see.
Over and over again for every single point on there, rather than calculating it to this point, that distance squared, which is way easier.
Yeah. Okay.
Okay, so it's going to make our integrals way nicer. And then we're just going to add some constant factor when we're done to shift it.
I see how it's way easier and that's useful to figure it out for the math. But I'm saying in the real world, when is it useful to know when an object like that is rotating around a point clear outside of it?
I mean, you open the door. There's
Yeah,
moment
but
of
that's
inertia
part
for the
of the
object
door.
pivoting.
That's part of the door, right?
No, if you think about a door opening, what's the moment of inertia? You know the moment of inertia for a door just rotating down its center, but that's not how a door opens. A door pivots clear out its left part. So how do you calculate that moment of inertia?
Oh.
Calculate the moment of inertia around the center of the door, and then plus the mass of the door times the distance from the center of mass to the end, so half the length of the door squared. There you go. There's moment of inertia for opening a door.
Okay, that makes sense.
There you go. All right, so I think we're ready to take the bull by the horns, wrap our heads around this theorem. This theorem is the only theorem in this section, by the way. So this is basically all the new material. And tomorrow I'll show you a few integrals. Anyway, so we've got some random shape. Who knows? Some weird shape. Since we're doing a proof, we can't assume we have any nice shape, right?
Yeah.
And we're just going to assume its center of mass is right there. Its center of mass has to be somewhere. So pick a point, we'll pretend that's the center of mass. Now the important part, I am going to choose my coordinate system. It doesn't matter what I call x and y, right? Physics doesn't care about what I call x being 0 and y being 0. So I'm going to choose my coordinate system so that my x and my y go through the center of mass. You with me?
Yeah.
Okay. So we got some random shape, there's the center of mass, and here's the point P that we're going to rotate this mass around. Some other point P. It didn't have to necessarily be inside the object. I just drew inside the object.
Okay.
Good so
See
far?
what's going on.
Okay. So our job now is we're calculating the moment of inertia rotating around that point P.
Okay.
Okay. So choose xy axis such that the center of mass is equal to the coordinate point 0, 0. Center of mass is our origin. Okay. Let P equal to, its coordinate points are A, B, whatever those are, we have no clue, be any point. Anywhere. Who cares? I happen to draw inside the object. There's no reason you have to do that. P is going to be the point that we rotate around. But notice now that we know that the coordinate points of P are A and B. Whatever those are.
Yeah.
Could be positive, could be negative. I happen to have drawn them positive. Okay. Now I'm going to say D is the distance from the center of mass to P.
Okay.
Good? So how do we calculate that distance? Since the center of mass is at the origin, then that's just going to be a squared plus b squared under the radical.
So just the Pythagorean theorem?
Just the Pythagorean theorem, more importantly, just the distance formula. The distance from any 2 points in the 2 dimensions, d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. You remember that formula?
Yeah.
And that is using the Pythagorean theorem, but there's a formula. And so my x2 is a, my x1 is 0, so a minus 0 squared is just a squared, and b minus 0 squared. Perfect. But we're going to use that distance formula again, so I just want to throw it up there.
Okay.
Okay, so let d be that distance. Now let mi be any mass at some point x sub I, y sub I. Some random mass.
Anywhere.
Anywhere on the actual object now. Because
Okay.
we're going to calculate the moment of inertia. What am I going to do? I'm going to take each of those masses, multiply it by their distance from p squared, and add them all up. And that's its inertia.
It's distance from P.
P. Yes, we're rotating it around P.
Okay, yep.
So I'm going to show that rotating it around P is equal to rotating it around the center of mass plus this constant. So we're calculating rotating it around P, and I'm going to show it comes out this way.
Okay.
So I'm going to take the distance all the masses are from P, take their distance squared from P, multiply it by the mass, add all those up, and show that comes out this way. You with me?
Mm-hmm.
Okay. So let m sub I be whatever piece of mass that we're talking about, and its coordinates are x sub I, y sub I, whatever those are, right?
Yeah.
So then r sub I, let r sub I be the distance from P to m sub I. So r sub I is going to be the distance it is from the point we're rotating it around.
Okay.
And, okay, so then our moment of inertia around the point P is equal to the sum of all our masses from I to n, whatever n is.
Missing anybody?
No.
Okay. Have fun.
Have to, I don't know, had like a flash to my night class for a second. That's weird.
Uh-huh.
Get them all mixed up in my head because you guys keep showing up to all my classes.
Crazy.
Anyways, so the moment of inertia around P then is equal to the sum of all the masses times their distance from P squared. Right? That's just a definition of the moment of inertia. Definition right here.
Yep.
Well, what is r sub I in terms of x and y?
Just the
So here's where we're using our distance formula. Remember, r sub I is the distance from P to m sub I. So r sub I is going to be x2 minus x1 squared plus y2 minus y1 squared.
I see it.
Good? Okay, so that's our definition of our moment of inertia around P. Side note, r sub I can be rewritten this way.
So you just plug it in?
So plugging in for r sub I there, so our moment of inertia around P is right here. I just replaced r sub I squared with this quantity squared, which just gets rid of the square root.
Yeah.
Good?
Mm-hmm.
Now I'm just going to distribute. I'm going to distribute in a little bit of a weird order, so let me show you where all the terms show up. X times x, that one's right there.
Okay.
X times negative a, and negative a times x, those two are right there. Negative a times negative a, that term's right there.
Okay.
Y times y, that's right there. Negative b times y and y times negative b, both those are right there. And then negative b times negative b, that's right there. So we talked about 6 terms total. 2 of them add together, so, well, yeah, 6 is what we should have when it's all said and done. And yeah, we have 6 terms. So you good with going from here to here, just expanding those out?
Yep.
Okay, now I'm just going to break them up into a couple of their own sums. I'm going to want these two summed together, that's why I changed the order. I'm going to put these two in their own sum, that in its own sum, that in its own sum, these two in their own sum.
Okay.
That's what I'm doing, going from this line to this line. So, mi times those ones, minus 2a, notice that 2 and a are constant, so I can just pull them outside the sum.
Yeah.
M times x sub I, coming from this one, mi x sub I, right there. From this term, we had mi y sub I, and we pulled out the negative 2b.
Mm-hmm.
And then this term, we have m sub I a squared plus b squared. You good with that one?
Can you pull those out?
Pull these out of this sum.
Yeah.
I could express it as 2 sums if I wanted. I could do mi times a squared plus mi times b squared.
Oh.
and then I could pull the a squared out of the first one and the b squared out of the second one. The short of it is I could pull those out, but I'd also have to distribute it, so it's two separate sums.
Yeah.
Okay. But we're not going to do that, but yes, you could. Okay, now just some substitutions.
Okay.
So first off, substituting out this term. The sum of all the masses times their distance from the center squared, from the center of mass squared, right?
Center mass.
Yeah, our center of mass was set up to be the origin.
That's right.
So x sub I is how far m sub I is in the x direction. Y sub I is how far it is in the y direction.
For any m sub I, right?
For any m sub I.
Okay.
So what's m sub I's different distance to the center of mass?
R sub I plus P.
Plus d, you mean?
Oh,
Is that what you're trying to say?
sorry. Yeah.
No, that's not it, because it just so happens that those look like they're going in roughly the same direction. I could have had my m sub I. Should have left this one and moved my p. But we could have also been talking about, let's leave that, because we'll make reference to it. When I'm talking about this point right here, this other m, its distance to p is this, and its distance to the center of mass is right here. This line.
Oh, I see. Would it just be your distance?
It's just its x coordinate plus its y coordinate squared
Okay.
Why are they
under the
squared?
radical. Huh?
Why are they squared?
Distance.
It's just regular distance formula of Pythagorean theorem. Draw on a separate thing over here. Here's my center of mass. Here's m sub I.
Yeah.
What are its coordinates? X sub I, y sub I. What's the distance from the origin to there? The square root of x sub I squared plus y sub I squared. Pythagorean theorem.
So how'd you get from it's squared x sub I plus y sub I?
Oh, thank you. I can't believe I did that. Yes, the square should be on the inside. That is funny. I didn't even notice that. Because I did it right there. No wonder you guys are confused. Okay, yeah. We didn't change anything going from here to here. We're just writing those two terms. Okay. So now it makes sense that this right here is the distance to m sub I squared.
Okay.
Does that make sense? Because the distance to m sub I, that's that thing. Square it, and you get this.
Yeah.
Okay. So in other words, this is the moment of inertia around the center of mass.
Yeah.
Mass times distance squared. Moment of inertia around the center of mass, because that was the distance to the center of mass. Good with that substitution?
Mm-hmm.
This substitution can't do anything for a second. This substitution can't do anything for a second. This substitution, notice that the square, or a squared, look back up here for a second. D is equal to the square root of a squared plus b squared.
Okay.
So if I square both sides, then that gives me this. So this is the same thing as d squared. You see that?
Where's your m coming from?
Now sum up all your little masses, that gives you the total mass.
Of
So I can
whole
take the
thing.
d squared, pull it outside the sum, and then sum up all my masses, which is just what we mean by capital M.
But why do you have a d? Oh. Your d squared with the dot looked like a d and a question mark.
Oh. Yeah. Alright. I see what you're saying. D squared, and then that's a period.
Yeah.
Okay. Make sense now?
Yeah.
Okay. So, notice how we almost had exactly what we were trying to prove. There's a moment of inertia around the center of mass. There's m times d squared. Now we just have these two pesky terms. What are we going to do with those two pesky terms? Well, let's go back to our definition of center of mass in the x direction really quick.
Okay.
Our center of mass in the x direction was take all the masses in the x direction, multiply it by how far they are in the x direction, their x coordinate, and divide it by the total mass. You take its mass times its distance, and you multiply it by and you divide by the total mass. You remember that?
Yeah, I do. That was.
You don't remember that? Draw out a picture really quick. If I had, can't remember what I used last time. That was a terrible line. If I have a mass of 10 at 0.1, and I have a mass of 2 at 0.6, where's the center of mass? I do the mass times where this one is. So here's 0 over here. I do 10 times 1 plus 2 times 6, and then divide by the total mass, in this case 12. Right?
Yeah.
So in this case we get 22 over 12, or 11 over 6. Which is going to be a little bit more than 2, right? So a little bit more than 2, which makes sense. Center of mass there. Coming back. Okay, so the sum of all the masses times their x position, divided by the total mass, gives you the center of mass in the x direction.
Yeah.
Moving big M over here, we get that the sum of all the masses times their x coordinate is equal to the total mass times its x coordinate, the x coordinate of the center of mass. Does that make sense? Just moving the M to the other side. Now notice in our special case, what is the x coordinate of the center of mass?
0.
0. We chose our coordinate system so that the center of mass was at coordinate x0, y0.
Okay.
So this sum comes out to 0.
Okay.
So this sum is 0. And for the same reason, except for with the y coordinate in the center of mass, this sum is also 0. Because we also chose our coordinate system so that the center of mass was 0 in the y direction. So that sum and that sum are actually 0. So that and that are 0. So we get rid of that, we get rid of that. What are we left with? We're left with moment of inertia around the point P is equal to I in the center of mass plus m times your distance squared. There's the big theorem.
Okay.
And so, the beautiful thing in doing it in one theorem like this is all the algebra that we had to do here in the canceling out is something you would have ended up having to do in every single one of your integrals that you calculated. All that algebra that we just did, converting from one point to the next point. So the theorem does all that algebra for you in one go, because it's always going to be the same algebra.
Yeah, that makes sense.
So the exact algebra that we did here is the exact algebra that you are now avoiding in all your integrals, which you don't want to have to do that algebra every time. So that's why it's useful. Okay, so there's that. So we'll move on to test questions, and then next we'll spend the rest of today for test questions, and then tomorrow we'll just do a bunch of examples. And you should have enough to get started on the homework. This is all the new material, except for the very end stuff where we actually calculate some integrals. So you can get started on homework if you want to. All right. Let's get going now with example problems. So we've been talking about moment of inertia, right? Well, actually, first we went over all those angular equations, which were very close to our linear equations, like the kinematic equations, but angular equations.
Yeah.
So we had theta equal to theta naught plus omega t plus 1/2 alpha t squared.
Is it omega not t?
Omega not t, thank you. And then we have omega is equal to omega naught plus alpha t. Then we have theta minus theta naught is equal to 1/2 omega plus omega naught times t. And then we have omega squared is equal to omega naught squared plus 2 alpha times theta minus theta naught, right?
Yeah.
Yep.
For basic equations. So the first example problems, not positive, but I'm guessing that they're going to be problems that make use of these equations. And then we'll move on to moment of inertia example problems. And then finally do some integrals, calculating some moments of inertia. So let's start with our first example problem. The angular position theta of a 0.36 meter diameter flywheel. So just get information as I'm reading this. It says my flywheel has a diameter of 0.36 meters, so the radius of my flywheel is going to be 0.18 meters. And it says my equation for theta is equal to 2 times t cubed. So that gives me my angular position at any given time, right?
Okay.
So we've got some flywheel. Well, it has some radius r. And it's spinning around. And let's just write down 2 more equations really quick here. So what is my omega equal to?
It's just the derivative of that. So
Perfect.
6t squared,
And what's alpha?
12t.
12t. Wonderful. So notice that whatever this flywheel, it's spinning around, but notice it doesn't have a constant acceleration. Right?
Okay.
Even the acceleration is speeding up with time. So this flywheel is speeding up very fast as it rotates.
Okay.
Good?
Yeah.
Okay. And obviously at time 0, how fast is it spinning?
It's not.
It's not. So it starts out rest and suddenly it's spinning up really quickly. Good? Okay. And so we have our radius, it's spinning around. Now what does part A want us to do? Part A, find theta in radians and in degrees at 2 seconds and at 5 seconds. Okay, so what is theta at 2 seconds? Well, that's easy. 2 cubed is
8,
times 2,
16.
so 16 radians. Now they also said convert that to,
Okay.
And then they said also convert that to degrees. How do you convert radians to degrees?
Pi over 180.
Pi over 180. So this is also equal to 16 times pi divided by 180 degrees. Because notice pi radians over 180 degrees is equal to 1, right? So multiply this by 1. Oh, oops, I did that upside down, huh? Sorry. Stink.
Oh.
16 times 180 over pi. Numbers should get bigger, not smaller. And what I have here written is true, but this is also true. 180 degrees over pi radians is 1, right?
Yeah.
And so when I multiply this by this, the radians cancel out top and bottom, so we just have 16 times 180 degrees all over pi. Right? Nothing weird. And then theta at 5 seconds, well, that's no secret. 5 cubed is
125.
times 2 is,
Oh, 5 cubed.
250.
yeah, 250. So 250 radians, or if we want it in degrees, that's going to be 250 times 180 over pi degrees, whatever that is. Good?
Yep.
Pretty straightforward?
Yep.
So that was part A. Find the average angular velocity in radians per second and revolutions per minute over the interval. Oh wait, I skipped it. That was just part A. So this is part A. Part B, start with part B next. Find the distance that a particle on the flywheel rim moves over the time interval from t1 equal to 2 to t2 equal to 5. So we've got some particle here on the flywheel. And this is where it is at 2 seconds.
Okay.
After 5 seconds, the wheel's going to spin a few times and it's going to end up somewhere else on the wheel, like right there, maybe. Right?
Yeah.
So here's where it was in 2 seconds. After, by the time we get to 5 seconds, we're somewhere right here. We want to know how far did that little particle move in meters.
Okay.
You with me?
Yeah.
So how do we get that?
We're just finding the displacement of the theta and then multiply it
Perfect.
by r.
We take theta at 5 minus theta at 2. That gives me my angular displacement.
Okay.
And we multiply by r.
Oh, yeah.
And that gives me my linear displacement. That will come out to whatever it comes out to, but you know how to get the number.
Yeah.
Good? guess can check our ones that we don't convert to degrees. 16 radians, 250 radians. Okay, we got that right. So I guess we can kind of get a feel for this one. 250 minus 16, what's that?
214? No.
Try that again.
234.
234. So we have 234 times r, which is going to be approximately, equal sign, which is going to be approximately, let's see, it gives 0.18 instead of something like 0.2. So we'll just make sure we're on the same page as them. 234, yes, times 0.18, and they say it comes out to 42 meters. We'll trust them. Okay, that was the linear displacement. Find the average angular velocity in radians per second. So part C, I'm looking for omega average over that time interval. How do you calculate omega average?
That's the change in displacement with the change in time.
Displacement over time. So our displacement we already calculated is 234 radians, right? Over our time,
3 seconds.
which was 3 seconds. Now, is that 78?
If you say so.
So 78 radians per second. Multiply by 3, see what you get.
Oh, yeah.
740. Oh, 78. I was looking at the wrong one. I guess there's 2 parts to B. Let me go back and find it. Or C. Find the average angular velocity in radians per second and in revolutions per minute. Okay, so that's radians per second. Now I want to convert omega average to revolutions per minute.
So what, you just times it by 60?
No.
Like 6.
We gotta sit here and multiply by 1 until we get revolutions per minute, right? So, first off, how many radians are in a revolution?
2 pi.
2 pi. So I can multiply this 1 revolution over 2 pi radians, right?
Okay.
And then I can multiply it by, we were doing per minute. And so I can do 60 seconds in 1 minute.
Oh, I see.
And then the radians will cancel out with the radians, the seconds will cancel out with the seconds, and we'll be left with revolutions per minute. So it's going to be 78 times 60 all over
2 pi.
2 pi.
Yep.
Which will come out to, just do that math really quick in my head, and should be about 740 revolutions per minute.
Okay.
Good?
Yeah.
Alright, part D, problem that never ends. Find the instantaneous angular velocity at 2 seconds and at 5 seconds. Okay. So now D, we're looking for omega at 2. Well, what's that?
It's just that.
24.
24. 24 radians per second.
Why is it 24? Oh. Yeah.
Instantaneous now, sorry. Instantaneous angular velocity. Did I say acceleration? I meant velocity. Or speed. Angular speed is what it's called. Okay, and then finally omega at 5. What's that equal to? 150.
Yeah.
25 times 6 radians per second. Okay. So that was the first example problem. Second example problem. For the flywheel in the previous example, find the average angular acceleration from 2 to 5 seconds. Find the instantaneous angular acceleration. Okay. So now part A for part 2. We're looking for alpha average, right?
Yeah.
And how do we calculate alpha average?
So change in omega over the change of time.
Change in omega over change in time. So perfect. So 150 minus 24 is
126.
Perfect. Divided by how much time?
3 seconds.
3. And that should be 42. And we're in radians per second squared. Right?
Yeah.
Okay, in part B, we're supposed to find the instantaneous angular acceleration at 2. What's that going to be? 24 radians per second squared. And then alpha at 5 is going to be
60.
60 radians per second squared. Sorry, that's an S, not 5. More like a 5. Any questions on that one?
No.
Alright, next one. You finish watching a movie on a Blu-ray and the disc is slowing to a stop. So you just open the disc player, Blu-ray disc is still spinning. The disc angular velocity at t equal to 0 is 27.5 radians per second. So we should probably erase this. We can keep the circle since we got a spinning Blu-ray disc. We're probably going to need its radius and stuff like that. Okay, so our initial angular speed when we opened the Blu-ray player was, I already forgot, 27.5 radians per second. And its angular acceleration is a constant, alpha, is equal to minus 10, if I read that right. Minus 10 radians per second squared. All right, so you know that alpha is a constant. What are we automatically thinking in the back of our head?
We can use kinematics.
Perfect, we can use those kinematic equations. A line PQ on the disk surface lies along the x-axis at time t equal to 0. What is the disk angular velocity at 0.3 seconds? What angle does a line make at 0.3 seconds? Okay, so we've got some line drawn on the disk. And it's at 0 degrees. We assume that the disk is spinning this way, I guess.
Okay.
So that's the line that they're talking about. So A, we're looking for what is the disk's angular velocity? I'm going to say angular speed.
This angular velocity.
I guess they call it angular velocity. What is the disk's angular velocity at t equal to 0.3 seconds? So what is omega at 0.3 seconds? Equal. And we're looking for in part B at 0.3 seconds. So we'll just call it omega at some future time. At 0.3 seconds, this thing's going to move, right?
Yeah.
And we're also looking for that angle. Well, we can't use theta. No, we can't use theta. Theta. So we'll call theta naught is equal to 0 degrees. You with me? So theta is going to be this angle, and omega is going to be the angular speed at that angle.
Okay.
Okay. So, and then we're also wondering what does theta equal? And we know that t is equal to 0.3 seconds.
Is everyone here today?
Yes.
Cool.
So, I think that's everything we need, right? Ready to start solving
Yes.
it? Didn't miss any information. Okay. So we're looking for the angular speed. Well, that's real easy. Omega is equal to what?
Omega naught
Omega naught
plus alpha times t.
plus alpha times t. And so this is going to be equal to, the disk is slowing down, right? So our omega is going to get smaller with time.
Yeah, sure.
So our omega naught is 27.5. And then we're going to have minus 10 times 0.3. Which is going to be what?
Just
Like 24.2.
24.5
Oh, yeah.
radians per second. subtracting 3, right?
No, because
What's 0.3 times 10?
3.333. Oh, never mind, you're right.
Okay. Okay, so now we're looking for theta. What's our equation for theta?
The equation for theta?
Yeah, theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. Okay. What's theta naught?
0.
0, so don't bother with that term. Omega naught is 27.5. So we have 27.5 times our time. So we got 27.5 times 0.3. Then we're going to have minus 10 times 1/2 is just going to be 5.
Yeah.
So minus 5 times 0.09, or 0.3 squared, right?
Mm-hmm.
That's right.
So, now I don't want to do the 0.3 times 27.5 in my head, so I guess we'll find the gal calculator. Oh, I left my backpack. So, we don't have a calculator. Unless one of you guys have a calculator.
Just use my phone, guys.
Yeah, you're both without your backpack.
7.8. You're saying is what this number is?
No,
Or did you do the whole thing?
I did the whole thing.
So this is equal to 7.8 radians. I just leave the book in the car.
So you never have to.
I just leave it in the room, but I'm afraid of accidentally leaving it in this room
Yeah.
when we need it in that room. Of course, that shouldn't be a problem. Okay, let's check. A, we got 24.5 radians per second.
Yep.
B, we've got 7.8 radians. Okay. Next, throwing a disc. So we're talking about an athlete just grabbing a disc and chucking it.
Okay.
Throwing a disc. So an athlete whirls a disc in a circle of radius 80 centimeters. So it's like the length of the arm of the athlete is 80 centimeters.
The length of his arm or the disc?
It's like the length of his arm is that. So here's the athlete's arm sticking out, holding the disc here. And he's gonna, so this is the center of him. Here's how he's holding the disc. He's gonna throw the disc. Okay. So as he's throwing the disc, he's gonna move on a circular arch, is what they're saying.
Alright.
So, and we know that this is 0.8 meters, right?
Yep.
Is the radius.
That's a long arm.
An athlete whirls a disc in a circle of radius 80 centimeters at a certain instant. The athlete is rotating at 10 radians per second. So at some instant in time, we'll call that time 0, omega naught. He's spinning at 10 radians per second.
Okay.
And the angular speed, see here they call it angular speed. And the angular speed is increasing at 50 radians per second squared. So alpha at this time is equal to 50 radians per second squared.
Why is it called angular speed?
It's always called angular speed, not angular velocity, just because we like to think about a velocity as being a vector, where speed is just a scalar. Angular speed is always just a scalar.
Why do you use acceleration for speed?
Yeah. Why not omega?
Oh, this is angular speed.
Oh, you said angular speed with the bottom.
Oh, no. I said, and the angular speed is increasing at 50 radians per second.
Oh.
The angular speed is increasing. So that's your angular acceleration.
There we go.
Yeah.
Good now?
Mm-hmm.
At this instant, find the tangential and centripetal components of acceleration find the tangential and centripetal components of acceleration of the discus and the magnitude of the total acceleration. Okay, so as this athlete is throwing this, first off, he's speeding up how he throws it, so there's an acceleration going this way, a tangential acceleration.
Yeah.
But since it's traveling on a circular path, there's also an acceleration this way, which is centripetal acceleration.
Okay.
We're looking for the resulting acceleration.
Okay.
Good?
Yeah.
So, tangential acceleration, this one's a stupid easy one. Tangential acceleration is just,
The acceleration times the radians.
yes, angular acceleration times r. It's just alpha naught times r. The centripetal acceleration is
Omega squared.
omega squared times r. Okay, and now you see this problem's gonna be easy. Right?
Yeah.
Right.
So, let's put the numbers in really quick here. Alpha naught, 50, times 0.8 is going to be 40.
Mm-hmm.
So this we have 40 meters per second squared. This one we have, let's see, 100 times 0.8, 80 meters per second squared.
Add them together, square them, and
Tangential, 40, radial, 80. Okay, so then the acceleration, the speed of the acceleration vector, or the magnitude of the acceleration vector, it's going to be the square root of these two things squared, right? And since I don't have a calculator, I'll trust that the author plugs in right, and he gets 89.4 meters per second squared.
Okay.
Good?
Very,
Very good?
very good.
Okay, propellers on a plane. Yeah, this is going to be tough for me to try and draw, but we'll do our best. So we've got some, I don't even know, never really drawn a plane before. We've got some plane, okay, it's got its wings, whatever, another wing on the backside. But at the nose of the plane is a propeller that spins. So there's blades on the propeller spinning around, right? Spinning around real fast. The plane's going to be moving forward, and then these are going to be rotating. So let's see what we're after. You're designing an airplane propeller that is to turn at 2,400 revolutions per minute. So our omega is equal to 2,400 revolutions per minute. We need to convert that to radians per second. We'll leave it like that for a sec. The forward airspeed of the plane is to be 75.0 meters per second. So the velocity of the plane, the velocity of the airplane, VAP, because I think I'll also want to use a subscript, just P for propeller. Okay, so I'll use AP for airplane. So the velocity of the airplane is to be, I already lost it, 75.0 meters per second.
That's not very fast. Oh, that's fast.
75 meters in 1 second.
I was reading it per minute.
Let's see. And the speed of the tip of the propeller blades through the air must not exceed 270 meters per second. So the velocity of our propeller spinning through the air, we don't want it to go over 270 meters per second, but we want to get as high as we can to that, so we're just going to say we want our propellers to be rotating at 270 meters per second.
Okay.
Or not rotating, but we want that to be their velocity. Now the point of that, the reason that why would you ever cap how fast those propellers spin?
And they just
The point is you don't want them, not just how fast they spin, but how fast, because they also move forward. Why do you want to cap the velocity of the tip of a propeller there? The reason is going to be so that you don't break the sound barrier, so that the plane doesn't get super loud. Because it's when you break the sound barrier that suddenly gets loud.
And that's a problem?
It's a problem if you want to fly the plane in certain areas.
Oh, yeah, because you don't want to hear the noise.
Well, can also
But it has nothing to do with the actual flight, right?
This is about 80% of the speed of the sound in air. If the speed of the propeller tips were greater than this, they would produce a lot of noise. Okay, so they're aiming for 80% the speed of sound,
Okay.
and it helps keep the plane a lot more quiet. Because once you break the sound barrier, that's the loud sound of a gunshot going off. Breaking the sound barrier, that's loud. It's not some sort of explosion inside the gun that's loud. It's a relatively small explosion.
Oh, really?
Yeah, it's the bullet traveling through the air that's so loud.
Oh, really?
Yeah. So, breaking the sound barrier is what's loud.
That's cool.
So, a bullet breaks the sound barrier, meaning that a bullet hits you before you hear the gun go off.
Good to know.
So, you couldn't duck.
If I hear any.
Even if you had instantaneous reflexes, you couldn't duck by hearing the gun shoot and drop. So, people who hear a gun go off and then drop to the floor, the bullet would have already hit you. Can't dodge that. The bullet goes faster than sound.
Interesting.
Crazy.
Yeah. Anyways, so we don't want the propeller of our plane to go faster than 270 meters per second. And I'm guessing how fast we want this thing to spin is what we're after. Oh, wait, what are we after? What is the maximum? Oh, we're going to say what's the radius we can make the propellers. So what is the radius of our propeller? That's what we're trying to calculate. What radius of propeller can we use? The bigger the radius, the better. The more thrust you'll get. Right?
Okay.
But we don't want such a high radius that we break the sound barrier. Because the bigger the radius of the propeller, the faster those outer tips move, right?
Okay.
So we know that the propeller is going to be rotating this fast.
Mm-hmm.
The radius then gives us the velocity that the propeller moves. Okay, so we have the velocity of the propeller. Now, how can I kind of draw this so that you can see it correctly? We'll think about the propeller when it's not up and down like that, but turned sideways like this. So when the propeller is turned sideways like that, thinking about this point right here, then it's moving down when the propeller, so think about this marker as a propeller, right? Right now I have it drawn like that. When the propeller's like this, think about this point, if the propeller's spinning this way. It's going to be moving down with some velocity.
Yeah.
Right? That point right there, on the very end, at this instant, it's moving down with some velocity, but it's also moving forward with some velocity because of the velocity of the plane. So the resulting velocity of those two velocities is going to be 270 meters per second. So I'm going to have this right here as the velocity of the airplane. This right here we'll call the velocity of, the velocity down, I don't know what to say, the velocity down. And the resultant is the total velocity of the propeller.
Oh, I see.
Does that make sense now? So you might have naively thought, you might have ignored the forward velocity and just said, oh, what makes so it's rotating this fast? You need to take into account the forward velocity of the plane as well. The total velocity of the propeller can't be over 270 meters per second. Not just the spinning velocity.
Oh, I see. That makes sense.
So we have to take both into account. You have to take into account that the propeller is moving forward and that it's spinning. And so no point on that propeller can go over 270 meters per second when you take into account all those velocities. Otherwise, it's going to start getting really loud. Does that make sense? Okay. So, well, no, I think you got it. So I need the velocity down. Oh no, we're calculating the velocity down. All right. Let's say the velocity due to spinning. Maybe that makes more sense. The velocity due to spinning. Okay. And let's convert this really quick. So 2,400, if that's revolutions per minute, I want to convert that to radians per second. So first let's get rid of the revolutions. We have 2 pi radians. I'm not doing equals, I'm going to multiply 2 pi radians by 1 revolution, right?
Yeah.
And then I'm going to multiply that by 60 seconds.
Per minute?
No, 1 minute per 60 seconds.
No.
1 minute per 60 seconds. Yeah, this is revolutions per minute is this. I should slide it right like this. Revolutions per minute.
Yeah.
Okay. So this is 1 minute. This is 60 seconds. And when you do all that, it should come out to 251 radians per second. 251 radians per second. Okay, so there's our omega. Now our velocity due to spinning is equal to what?
It's the omega times the r.
Omega times r.
Omega times r.
Yes. Your angular speed times r.
Isn't your total velocity equal to that though?
No, that's the speed. Look, imagine that the airplane's not moving.
Okay.
That means that this velocity is 0. Now the velocity of my propeller and my velocity due to spinning are the same thing. This one right here is just my velocity due to spinning.
Oh, okay, I see.
Good?
Yeah.
So our velocity due to spinning, this fact that the propeller is spinning, is just omega times r.
Okay.
Right? Now, I know that the total velocity of the propeller, we'll say squared, is equal to the velocity of the airplane squared plus the velocity due to spinning squared, right?
Mm-hmm.
This is what I'm trying to solve for r.
Yeah.
We're trying to figure out the radius.
Mm-hmm.
So ultimately I'm trying to solve for r. So first I'll solve for bs, then I'll solve for r.
Okay.
So the velocity due to spinning is equal to the square root of the velocity of the plane squared minus the velocity of the propeller squared minus the velocity of the airplane squared, right?
Mm-hmm.
And so now we get r is equal to the square root of the velocity of the plane squared minus the velocity of the propeller squared minus the velocity of the airplane squared, all over omega.
Gotcha.
And so the velocity of the propeller squared, that's 270 squared. The velocity of the airplane squared, that's 75 squared. And then omega, that's 251. You plug in all those numbers, and what comes out is 1.03 meters. So that's the radius of that propeller. That's the max radius you can put on that propeller to satisfy these conditions. Make sense?
Yep.
Okay. Moment of inertia. We'll calculate one moment of inertia discretely, and then we'll do it with some integrals, finally. The part you guys have been waiting for, right?
Yeah.
Let's remind ourselves of the definition of the moment of inertia. The moment of inertia is equal to the sum from, I think they typically use an I equals 1 to n of m sub I times r sub I squared. Add up all your masses times the distance they are from the axis of rotation squared, and that's your moment of inertia. Will you remember this?
Yeah.
Yeah.
Okay. So, next one.
Next
A machine part shown in the figure. Oh yay. So I have to draw this figure for you. So we have a block here, and then a line comes over, a block here, a line comes up, a block here, a line comes over. We're assuming that whatever's connecting these blocks together has no mass. These are all supposed to be straight lines. That's terrible. Anyways, we know the dimensions. This line right here is 0.3 meters. This line right here is 0.4 meters. And then obviously this one has to be 0.5 meters. So it's a right triangle. It's supposed to be a right triangle. My picture's lying a lot. This one has a mass of 0.1 kilograms. This one has a mass of 0.2 kilograms. And then this one out here has a mass of 0.3 kilograms. Good? Mm-hmm. Okay, so there's a picture A. What is a body's moment of inertia about the axis through the center of disk A perpendicular to the plane of the diagram? Okay, so they call this one A, they call this one C, they call this one B. Okay, so they're saying, now imagine we stick a rod through A, and we rotate these pieces around that rod this way.
Gotcha.
You follow me there?
Yeah.
So what's the moment of inertia for part A? The moment of inertia then is going to be, we sum up each mass times how far it is from the radius squared.
Mm-hmm.
How far is this mass from the radius?
0.
0, so that doesn't even come into the picture. So for this one, we have 0.2, its mass, times its radius squared, plus this one, 0.1, the mass, times its radius squared. Right?
Yeah.
And for this one, fortunately, I think we don't need a calculator. So that one's going to be 0.032, right?
Yeah.
Plus, and then this one's going to be 0.025.
0.0. Yeah.
Right? So when we add those together, we get 57. Did I do that right?
Mm-hmm.
So 0.057, part A, 0.057 kilogram meters squared.
That's what.
Because it's one mass and two distances, right? Excuse me. Mass times distance squared. Okay, so that was part A. Part B now. Let's calculate the moment of inertia when we stick our rod a different way and rotate it a different way. B, what is the moment of inertia about the axis through the center of disk B and C? Okay, so now we put our rod right here, in B and C, and we rotate it so this comes out of the board like that. Right?
Yes.
So the only thing rotating is A?
This is the only thing rotating. So in that case, it's just going to be
0.
0.3 times 0.16, right?
12.
Yep.
Equal to 0.3 times 0.16, which is going to be equal to 0.048 kilogram meter squared. Did I do that right? Check with the book. B 0.048. Okay. Part C. What is the body's kinetic energy if it rotates about the axis through A? Didn't say perpendicular to anything, so I assume sticking it back into the board like that before, even though they're not making that explicit. Through A with angular speed omega equal to 4 radians per second. So C, we're using our moment of inertia from part A, so I know that my moment of inertia is 0.057, right?
Yeah.
And now I know that omega is equal to, I already lost it. And now our job is to calculate the kinetic energy.
Well, that's just easy.
What's the kinetic energy?
1/2 inertia plus omega squared.
Times
Omega squared.
omega squared. But yeah, I think you have the right idea. Perfect.
Okay.
So you just plug in those numbers, and it comes out to 0.46 joules. Any questions on that?
That took like no energy.
Yeah.
It's a small mass.
Yeah.
It's true.
Okay. Good?
Yep.
Okay. So now let's do some integrals.
Okay. Just do that an infinite amount of times.
Huh?
Just do that an infinite amount of times.
Do an integral an infinite amount of times?
No,
Oh, I see what you're saying. With an integral. So on page 291 of your textbook, you're probably not going to remember that page, but it gives you the moment of inertia for a lot of different objects. Common shaped objects that we come across in physics.
Okay.
So one of them, I don't know if I want to draw all these for you, just show you the picture. Wow. Show the camera first. Show you guys and the camera, so come where you can see. So we got a long rod where the axis of rotation goes through the middle of the rod. Okay, so rotating about that. A long rod where the axis of rotation is at the very end, so that's kind of like a door.
Yeah.
Piece of wood or board, something thin but with longer dimensions, where we go right through the center or we go through one of the ends. Rotating around a cylinder hollowed out, then a solid cylinder, then a cylinder with almost no shell at all, and then a sphere, and then a hollow sphere. And it gives you the moment of inertia for each one in here. So you're not expected to calculate those. You're expected to
No.
just look up the shape in the table. Now, I don't want to take time to do integrals for all these, but we'll do a couple, so that you can get a feel for how these things go.
Okay.
So we'll start with the long rod, I guess. So we've got the long rod one. Like that. And we'll start with going through the center, because why not? So here's our axis of rotation. And we're going to calculate the moment of inertia of this thing, given that we know the mass of the rod, so assume that we know the mass of the rod and the length of the rod. And what's important here is that the rod is really skinny relative to its length. Because we're going to make an assumption there, which is a bad assumption, but, well, no. Never mind.
Okay.
Anyways, so we need to calculate the moment of inertia of this rod. Now we know how to calculate the moment of inertia. The moment of inertia is equal to the sums of all the masses times the radius squared.
Yes.
So I need to do some sort of integral, because there's going to be an infinite number of them, times, for each little mass, I need its radius squared, how far away the mass is, times that little bit of mass, dm, an infinitesimally small amount of mass. Okay, for every little piece of mass, and that's going to give me my moment of inertia. In general, that's the equation we use, and then you just think about how to make that equation make sense for your particular problem,
Gotcha.
right? So, let's think about in our case. In our case, thinking about dm is going to be some little sliver of mass. I'm going to cut some teeny tiny disk out of there, some infinitesimally small disk out of that thing, right?
Yeah.
Let's see how I'm going to want to do this. I might be overthinking it, because I'm thinking, assume it's a solid, but, let's see, dm because the mass is going to be uniformly distributed, And so some small piece of mass, okay, so dm over dx is going to be equal to mass over length. That's what I'm going to say. So I'm going to be going in the x direction, so dm has a width of dx. I'm going to be integrating from left to right across my d-axis. Okay, you with me?
Yeah.
So in our case, our radius is just going to be our x coordinate, how far out you are. So this is the general formula. For the actual integral that we're going to calculate, we're going to be doing the integral from, we'll call this position, we're going to go from negative L halves to positive L halves, using our coordinate system right down the center like that.
Yep.
Of our radius is going to be x squared,
Okay.
and then we need to do times dm, and I'll figure out what dm is here in a second. But the point is, since my mass is uniformly distributed, each little piece of mass, each dm, how's the right way to say this? I have this much mass m over this length L, right?
Yeah.
So what if I wanted to figure out how much mass half the rod has?
Just divide it by 2.
I would multiply this by 1/2, or divide by 2, right?
Yeah.
But if I want to know a smaller piece, like how much 1/3 of it has, I multiply it by 1/3. If I want to know how much mass was in a size that was dx in width, it's dx times that.
Okay.
Does that make sense?
Yeah.
I don't know if it's easier to think about it that way or to think about the ratio of infinitesimally small mass to its infinitesimal width is equal to the ratio of the whole mass to the whole width.
First one is better for me.
Yeah.
Okay, whichever one, this one makes more intuitive sense to me, but as I was saying that, I got the feeling you guys might like it that way. Either way, doesn't matter which one you use, you can now solve for dm.
Yeah.
Okay, so either way, this is equal to the integral from minus L halves to L halves of x squared times dm then is capital M divided by L dx, right?
Okay. Can you take m over L out of it?
Yep.
Okay.
So m over L, that's just a constant, so we have m over L times, what's the integral of x squared?
X cubed over 3.
X cubed over 3, and we need to integrate that, or evaluate that from negative L halves to L halves. Right?
Yeah.
And so that's going to be equal to, still m over L times, I'm going to pull out that 1/3 as well. So put that 3 there. You with me?
Okay.
So now I'm just going to be plugging that into x cubed. So when we plug in L halves to x cubed, we get L cubed over 8, right?
Mm-hmm.
And then when I plug in negative, minus, and then when I plug in negative, that's going to make this a plus, L cubed over 8.
So that's just what? 2 L cubed over 8?
So, 2. An eighth plus an eighth is a,
16.
2 eighths.
which is
A fourth.
a fourth. Okay, so we have 1/4 times 3 is 1/12. So I get, I have a sense I'm losing you guys, so let me just.
No,
write it
no,
down.
I think
You're with me?
Yeah.
L cubed over 4.
Okay.
Good? Okay, that L cancels with one of those L's. The 3 and the 4 come together. So the 3 and the 4, that's going to be 1/12. And then we have m times L squared. Follow that?
Yeah.
And you look it up in your book. 1/12 m over L squared. Or 1/12 m times L squared. Okay, we did it right. Woot.
Go us.
Alright. So now, let's try, let's just adjust this one since it's so easy. And let's just say, okay, let's pretend we were rotating about this axis now. You with me?
Yeah.
So all you're doing is you're changing.
So now I'm going to call this my xy axis right here, right? So all we're changing is 0 to L, which is what I'm guessing you were thinking.
Yep.
0 to L, 0 to L, 0 to L. But now when we plug that in, we're going to get, this is going to be equal to, I'll pull the 3 out once again, so we have m times L over 3. And now we need to evaluate L cubed minus 0, which is equal to, L's cancel out, we get 1/3 mL squared.
Okay.
Right?
Yeah.
Now, I may come up with this number another way, just to remind us of our theorem from yesterday. Our theorem from yesterday said that the moment of inertia through the center of mass is equal to the moment of inertia at any point P plus the total mass of the object times the distance squared, where d is the distance between the center mass and P.
Yeah.
We proved this
I know,
yesterday.
but isn't the center of mass and P switched, or do I have that
Thank
wrong?
you. You are correct. Good. Good eye. Yes. Okay, so the problem before, when we calculated it when the axis was right here, we got the center of mass. So I drew the center of mass before we calculated that that was 1/12 the mass times L squared, right?
Yeah.
Yeah.
Now, let's say for this axis right here, that's the moment of inertia through this point P, right?
Okay.
So now we'll use this equation to come up with that same number once again. Just to remind you of the equation. Okay. So the moment of inertia through P then is equal to the moment of inertia through the center of mass plus the mass times the distance between these two squared. What's this distance?
L over 2.
L over 2, and we're going to square it, so we're going to get L squared over 4.
Okay.
You with me? And then, that's equal to, this is 1/4 ml squared, this is 1/12 ml squared. A fourth plus a 12th is a
What's a fourth plus a 12?
1/3.
Yep.
1/3 ml squared, which is exactly what we calculated.
Oh, so you didn't need to go through all the integral work. You can just use that.
You should have done it either way. It's such a simple integral, I'm not sure which one was easier.
Oh, you just showed
One
us
was
what
just
it
changing the bounds, the other one was just adding this number.
Why did you only do half one, half D?
Sorry, what?
Why did you only do L halves?
This distance, the distance, here's the center of mass of this sink. Here's P. Here's center of mass. What's the distance between P and the center of mass?
1/2 L.
L over 2. And we have to square it. L squared over 4.
So the D is the distance between.
The distance from the center of mass to the point P you're talking about.
Yeah.
Good? Yep. Okay. I think some of the example problems will have us do other of those integrals, so we'll just wait till I come up in example problems. But give you a general idea of how these things work and how you calculate moment of inertia for a solid object, right? Yep. Okay, so next problem. We wrap a light, non-stretching cable around a solid cylinder of mass 50 kilograms. So here's my solid cylinder. We're just looking at it from bird's eye view, but it's a solid cylinder. And it has a mass of 50 kilograms. And since it's a solid cylinder with mass 50 kilograms, I'm automatically thinking in the back of my head, okay, so its moment of inertia is, look it up on the table, solid cylinder, 1/2 mr squared. 1/2 m r squared. We'll get the r here in a second. Probably should have not did that because they're going to have to tell us what that is. So I'll just write m is equal to 50 kilograms here. And then our radius, they'll tell us, I assume, or maybe it's in the picture. Our radius is 0.6 meters. 0.06. Okay, there's our radius. So times 0.06 squared.
Okay.
Just keeping things in mind. All right, so we wrap a light non-stretch cable around a solid cylinder of mass 50 kilograms and diameter 12 centimeters, or in other words, radius 6 centimeters, which rotates in a frictionless bearing about a stationary horizontal axis. We pull the free end of the cable with a constant 9 Newton force for a distance of 2 meters. It turns the cylinder as it unwinds without slipping. The cylinder is inertially at rest. Find the angular speed and the final speed of the cable. Okay, so we've got a cable wound up around the sink, and we start pulling the cable. And we pull the cable out from the sink 2 meters.
Yeah.
Now while we're we're doing that, the force that we were applying this way
9
was 9 newtons.
Okay.
And then we're supposed to calculate a bunch of different things. But before we calculate all the bunch of different things, let's just think about high level how we're talking about this. We're calculating energies, right?
The energies?
Uh-huh.
You mean like the kinetic and potential?
Well, ultimately we're getting velocities, but we're going to get that from energies.
Okay.
So I know that always and forever this equation, the initial potential energy plus the initial kinetic energy plus the work that goes into the system is equal to the final potential energy plus the final kinetic energy. Our universal equation whenever we're dealing with energies. Initial potential energy, 0. Initial kinetic energy, 0. We just have a problem where work is going into the system.
Yeah.
The work is going into the system, we apply 9 newtons over 2 meters.
So 18.
So 18 joules is our work that goes into the system.
I know. Okay.
Good?
Yeah.
Equals our final potential energy, 0, plus our final kinetic energy. Our final kinetic energy is 1/2 I omega squared.
And what are we trying to find? Omega?
Omega and velocity, which we'll get once we have omega.
Okay. I see.
Right?
Yep.
Why is it omega?
1/2 I omega squared.
Mind.
Okay. The formula for kinetic energy with the spinning object. So now we're looking for what's omega then? So omega is equal to, multiplied by 2 gives me 36, divided by I, take the square root.
Yeah.
Good so far?
Yes.
Okay. So let's see, omega equals 2 times the work, which is what we did, divided by I. So we did 2 times 18 divided by 0.09. So they say that this comes out to 0.09 kilogram meters squared. And so this whole thing comes out to, when you plug that all in, 20. And that's going to be radians per second. So that's omega. Right?
Yeah.
Now we need the velocity. What's the velocity? It's just omega times r. Which is going to be,
106.
I don't remember where we wrote our omega.
Our omega's right there. 20 radians per second.
Ah, thank you. So 20 times r is 0.06, so what do we have, 0.12? Is that right? No, 1.2, sorry. 1.2. Way off. There we go. Right? Double check with them. 1.2 meters per second.
Yeah.
Okay. That's it. That's all they were after. Another example problem, a little bit more complicated. It's going to have a similar thing. I don't know, we know the radius on this, so we'll just put an r there for now. But what's happening is, we are going to have some wound up cord around this thing, same as before, but then the wound up cord is coming down and it's going to hold up some mass, little m. And I think that the big wheel has mass big M. So this has mass big M, this has mass little m. It's held some distance h above the ground.
Okay.
And then we're going to let it fall, which is going to spin this thing, and we're going to calculate some speeds of things, I'm guessing. So now I'll read the problem. I'm just guessing from the picture. We wrap a light non-stretching cable around a solid cylinder. Solid cylinder. Is it 1/2 for the solid cylinder?
Yeah.
Okay. We wrap a light non-stretching cable around a solid cylinder with mass big M, radius r. The cylinder rotates with negligible friction about a stationary horizontal axis. We tie the free end of the cable to a block of mass little m and release the block from rest at a distance h above the floor. As the block falls, the cable unwinds without stretching or slipping. Find an expression for the speed of the falling block and the angular speed of the cylinder as the block strikes the floor. So how fast is the block going right as it hits the floor, and what's the angular speed of this sink?
Okay.
Now, this one's going to be a bit trickier because our kinetic energy goes into two places. But once again, we use our catch-all formula. U naught plus K naught plus work that goes into the system is equal to U1 plus K1. Right?
Yeah.
What's the potential energy of the system?
MGH.
MGH. Right? However, just gravitational potential energy of this box, there's no potential energy here.
Okay.
Plus, what's the initial kinetic energy?
There isn't any, right?
0. What's the work going into the system?
Just
0. No one's doing any work on the system.
well, gravity.
That's potential energy.
Oh, I see. Okay.
Okay. So this is equal to, what's the final potential energy of the system?
0.
0. The way we set it up, the box is going to be on the ground. We call that 0 potential energy. What's the final kinetic energy of the system?
1/2 mv squared.
We have 1/2 little mv squared plus 1/2 I omega squared. Because this has kinetic energy and this has kinetic energy.
Oh, so it's split into 2 parts.
Yeah. So that's a gotcha with a problem like this.
Okay.
Okay. Now, we're just solving for V. Let's plug in I really quick. So we have mgh is equal to 1/2 mv squared plus 1/2 times 1/2 is going to be 1/4, right?
Mm-hmm.
And then we have big M. Omega squared times r squared is v squared.
Oh, that's easy.
See that?
Mm-hmm.
Okay. So then we get mgh is equal to 1/2 m plus 1/4 big M all times v squared. Just factor out the v squared.
Yep.
So v squared is equal to that divided by that, and take the square root.
Yeah.
Oh, other way. We have mgh. Let me see if they do something. Yeah, they do. So something that you might not have thought to do, doesn't change the answer. Just something that they're going to do for convention. They're going to divide both sides by little n. So
Does that
dividing
make it
two,
easier?
it just makes that little n only shows up in one place rather than two places.
I see.
So we have GH is equal to 1/2, and then we have plus big M over 4 little m
Yeah.
times v squared. And let's see, are they going to multiply by 2? Yes, they also multiply both sides by 2.
Okay.
So just to, that one's kind of a nitpicking, but okay. So 2GH is equal to, when we multiply that by 2, it's just going to be 1 plus big M over 2 little m v squared.
And then,
And now we'll solve for v.
okay.
And so now v is equal to the square root of 2GH divided by 1 plus big M over 2 little m. And there's our expression for velocity.
Mm-hmm.
And then I don't know why we need an expression for angular speed, because angular speed is just velocity divided by r, and I don't want to rewrite that.
Yeah, that's pretty straightforward.
Good?
So just watch for kinetic energies.
Yeah. Make sure you account for all your energy. That's always the hard part. Okay, parallel-axis theorem, we did that. We already did a better example of parallel-axis theorem. We'll just go into this example. Okay, another one calculating momentum. This one we're going to calculate the moment of inertia, not momentum, moment of inertia for a cylinder with a middle piece missing. So I'll draw a bird's eye view and then a terrible two-dimensional representation of the scene. Well, I'll draw a 3D one and then a terrible two-dimensional representation. So we've got the cylinder. So it's going to look like this. That comes down, like that. And then it's going to have a middle part missing. So it's also going to look like this. So this part's the solid part, and then there's a hole in the middle.
Yeah.
You with me?
Mm-hmm.
Okay, and we're given that the distance from here to here, this distance is radius 1, and then this distance is radius 2. Our job is to calculate the moment of inertia for rotating around its center of mass. Okay?
Okay.
Now I'm going to draw a terrible two-dimensional version to make math easy. So our terrible two-dimensional version looks like this. Here's our coordinate system. Here's R1. Here's R2. And then here's the thing that we're rotating. We're taking that and rotating it around. Good?
Okay, that makes sense.
Okay, so moment of inertia of this thing. First off, we're assuming that this thing is uniform in density. Uniform density. We're assuming that any little piece of mass, if I grab the same size of mass, it has, or if I grab the same size of this cylinder, it has the same mass. If I grab 1 cubic centimeter from the top and 1 cubic centimeter from the bottom, those both weigh exactly the same.
Okay.
Good? So we assume that everywhere it has the same density, and we use rho to represent its density.
Is that the same with all the other problems we've done?
Yeah, we just didn't, it was easy to do it without ever even considering it. Like for that one, I just took the mass and divided it up. But, so here we'll use the fact that this has a consistent density of rho everywhere.
Okay.
And density is like mass per cubic meter. Okay. Yeah. So, moment of inertia of this thing. So, always and forever, our moment of inertia is equal to the integral of r squared times dm, right?
Mm-hmm.
Our radius here is going to be in the x-axis. So I know that for our case, the moment of inertia with how I've drawn this problem, completely convention how I drew the problem, I could have just as easily drawn it this way and used y's for my radius. But I'm setting it up so that we are doing an integral from r1 to r2 of x squared times dm.
Okay.
Okay, the little segment of mass that I'm going to use, since I just want to go from r1 to r2, notice that we have to be careful not to ignore the other piece of it over here, right, when we rotate it around.
Yeah.
So since I'm just going from here to here, I'm going to use cylindrical shells. I'm going to use cylindrical shells. So I'm going to take a little slice here, some little slice of this thing, which wraps around and also is a slice over here, right? Some really thin shell.
Yep.
And the mass of that infinitesimally small shell is going to be my dm.
Okay.
So my dm, my infinitesimal mass, is my density times my infinitesimal volume. An infinitesimal volume times the density gives you your infinitesimal mass. This is my volume, this is my mass per volume, so it gives me my mass.
But you're looking for dx.
I need to substitute dm there.
Yeah, but you
With
can
something that has a
substitute.
dx in it.
Yes.
We'll get there.
Okay.
We're going to get that from dV. We're going to do this the same way you've been doing it. You know how to calculate the volume of these things. You've been doing that with integrals all through calculus, cylindrical shells method. So that's the point, is the dV, that's something you already know how to do. What is the volume of that infinitesimal shell?
The volume of it?
Uh-huh.
I don't remember.
The volume of an infinitesimally thin cylinder. We take the area of the cylinder and we multiply it by an infinitesimally small width. What's the area of the cylinder?
Oh, isn't it 2 pi times the area?
No, you're calculating the area. So we're talking about some really thin cylinder, right? So here's some cylinder made out of a very thin material.
Yeah.
Very thin. It has some radius r. What's the surface area of that thing?
It's the 2 pi times the height.
It's
2 pi r.
the length of the top times the height. It's like you unroll it. If I unroll this, then it's just a rectangle, right?
Yeah.
What's the distance right here? 2 pi r. What's the distance right here? The height of this thing. Oh, we didn't put a height on here, did we? They're going to have to give us a height. So we know that it has a length L. So this is L right there.
Oh, I see.
And then some arbitrary thickness, which our arbitrary thickness for how we set this up is dx.
Yes.
Okay, so this is going to be equal to 2 pi r, in our case r is just your x coordinate, 2 pi r times L times dx. And so we converted our dm into a dx, which is what we were after, right?
Yes.
And now it's a stupid easy integral. So we're looking for I is equal to the integral from r1 to r2 of x squared times, oh sorry, that was just a dv. Don't forget our rho out here in front.
Okay, that makes more sense.
Okay, yep. That was just dv, and then we still have rho.
Okay.
Good? Sorry, that's a Greek letter rho, looks a lot like p. Common, that's what you use for density. So we have rho times 2 pi times x times L dx, right?
Okay.
Now we have an absurd amount of constants. Let's pull out all our constants. So I'm going to write my 2 pi first, then my rho, then my L. So those are all just constants. Times the integral from r1 to r2 of x cubed dx.
Okay.
And now you know how to take that integral. So this is going to be 2 pi rho L times r2 to the 4 over 4 minus r2 minus r1 to the 4 over 4, right?
Yeah.
Which is equal to, pull the 4's out, so that's going to replace it with the 1/2 out front, right? Okay, so we'll have 1/2 pi rho L times r2 to the 4 minus r1 to the 4. Did that right? Okay. Let's see. Okay, they want to rewrite it in terms of the volume and the total mass. So let's think about that. So let's just calculate the volume of the cylinder really quick.
Okay.
So when we calculate the volume of that thing, we'll do that over here. V is going to be equal to the integral from r1 to r2 of, now it's just, we're just integrating dv, right? To find the volume.
dv, yeah.
In short, volume is equal to the integral of all the little, out of infinitesimally.
Yeah, okay.
Yeah. Okay, so all our dv's, but our dv, nothing's changed. It's 2 pi x L dx. So 2 pi L x dx, right?
Yeah.
So when I integrate that, then I get v is equal to, we'll pull the 2 pi L out, and we're going to have x squared over 2.
Yep.
I'll just write it like this. X squared over 2, evaluate that from r1 to r2. Good?
Yeah.
2 cancels out with 2, so v is equal to pi L times r2 squared minus r1 squared. Good?
Yeah.
Now notice over here, now we have a pi, let me factor this out real quick and then you'll see it. So we have 1/2 pi, let's write our rho first, try and group the terms together that we're going to be replacing. Rho times, so 1/2 rho, we need pi in the L. Pi in the L times, I can factor this thing, that's going to be r2 squared minus r1 squared times R2 squared plus R1 squared.
Okay.
Right? And now notice pi L R2 minus R1 squared. This part is just a volume. So now this can be rewritten as I is equal to 1/2 rho times the volume times R2 squared plus R1 squared. Good?
Yeah.
Now if you want to write it in terms of its total mass,
It's total mass.
yeah, the total mass, rather than its total volume. So here's what it is in general, right?
Yeah.
We have it written this way. We said, well, if you want to write it in terms of its volume, here it is. What if you want to write it in terms of its total mass? What's the total, in terms of its total mass, big M? What is the total mass of that object? It's just the mass per volume times the volume.
Mass per volume times volume?
Yeah, rho is density, which is mass per volume.
Yeah.
So this is kilograms per meter cubed,
Because it cancels
and
out.
this is cubic meters.
Yeah.
Okay. So this is also, we can also write I is equal to 1/2 the total mass R2 squared plus R1 squared, which was a formula that you'll see if you look it up on your paper.
Oh, okay.
Okay. Things to notice, really quick. What happens if our R1 was 0? So notice if I make my R1 0, then now we just have a solid cylinder.
Yeah.
Yeah.
So if we make our R1 0, we just have a solid cylinder, so let's see the effect that that has on this. So we would be doing 0 to there, we would have done 0 to there, we would have done R2 over 4, right?
Mm-hmm.
Would have just been R2 over 4. Kind of ignore the rest of that. No sense factoring anymore. R2 over 4. When we calculated our volume, would have been a 0 there, would have been a 0 there, would have been just a R2 squared there, right?
Yeah.
So when we come and we replace that, we get inertia is equal to 1/2 rho, the pi L and 2 of those gives us our volume, times R2 squared. Replace that with the mass, and we get I is equal to 1/2. We don't really need R2 anymore since it's just, there's only one radius.
Mm-hmm.
That's our mass, so 1/2 mass times R squared, which was moment of inertia for a solid cylinder. Good?
Yep.
So, did a couple calculations for some of those formulas, how those formulas come to be. They do one more for a solid sphere, but I think you get how these go. You don't actually have to calculate those integrals, you just have to use those formulas.
Okay.
So we're good?
Pretty good.
Is that all of the new stuff?
Yep.
Okay.
Yep, that finishes it all up. So